Hi everyone. So this is the first of several videos about AVL trees. And in this video, I'm simply going to give a brief overview of what AVL trees are and the motivation behind having these AVL trees to begin with. So if you already know all about the basics of an AVL tree and just want to kind of get to the more meatier material, feel free to skip this one. So in a so before we talk about AVL trees, let's take a look at the problem of how regular binary search trees create trees. Okay, so if we were to use the regular binary search trees insertion algorithm on this set of numbers right here, what is what tree would we get from it? Well, regular binary search tree says we simply find the place where a value goes and we insert it into that position. We don't change any other parts of the tree. So 40 is the root. 20 is smaller than 40. So it goes to the left-hand side of 40. 60 is bigger than 40 and there's nothing to the right. So we put 60 to the right of 40. 30 is smaller than 40, but it is also bigger than 20. So we end up putting it to the right-hand side of 20. 50 is bigger than 40, but smaller than 60. So we put it to the left-hand side of 60. And if we keep doing this, we will end up putting 10, 70, and finally 80 into this position. Okay, and this is just following the regular binary search tree insertion algorithm. Now, if we were then, so this is the tree that we get. Okay, fine, right? Now let's suppose that I give you exactly the same data, but I give it to you in sorted order instead. So from smallest to biggest. So instead of inserting it in the order 40, 20, 60, 30, etc., we insert it in the order 10, 20, 30, 40, all the way up to 80 in order instead of this other way. Now, 10 would be the root, right? And then 20 would be bigger than 10, so it goes to the right. Then we have 30, which is bigger than 20, so it goes to the right of 20. And we simply insert in order, right? So 40, 50, 60, 70, and finally 80. All of them is now inserted into the tree. Now, what you can see is that I actually get two very, very different shapes on this tree. Now, this tree is actually really small. It only has 8 nodes. But you can see that there's actually a very different shape. And the left-hand side shape is more tree-like. And the right-hand side shape looks like the tree, well, sort of had all its branches cut off, and it's basically just a stick, right? So it doesn't really look like a tree anymore. Now, not looking like a tree is actually really problematic. The reason that we have binary search trees is because it supports searching. Like that's the whole point. That's why the search is in the name, okay? So if it doesn't support searching, we actually have a problem. So with a nicely shaped tree like the one on the left, what happens is when you do searching, you start the root and you can compare it against the value at the root, and either it'll be smaller or bigger. But either way, you basically eliminate half the tree right off the bat. Then you go down the subtree and you can eliminate half of the remaining tree. And you go down one more node and you cut off a half of the remaining tree from there. So you end up basically taking your data size that started like this, you cut it in half, then you cut that in half, and then you cut that in half, and you very soon get to very few nodes that you actually where your data might actually be. But if your tree looks like a stick, what you basically have is a linked list, a sorted linked list. And searching a sorted linked list is still ON, okay? So if you have a binary search tree that looks nothing like a binary search tree, looks like a stick, you do not have fast searching. It is as simple as that. So we have a problem because right now you can't guarantee that your trees are going to look like the one on the left because you have no control over how the data is put into the tree. You don't know what order they're going to come in. And it is not, and you can't say, well, I'll never get it in sorted order because that's not going to happen. Like having data that is pre-sorted is usually a good thing. So the fact that your tree can't handle it is actually problematic. So what we want is we want to actually have all our trees always looking sort of like the one on the left and not the one on the right. Okay, we want the one that looks like a tree, not the one that looks like a stick. So what does that mean? Well, it means that we actually have to alter the way that we create our trees. And there's different ways to do it within binary search trees. So we're going to look at two different ways. The first way is to use something called an AVL tree, to create something called an AVL tree. Now, before we begin with what all this means, I want to start off with a basic definition of an AVL tree, sort of to go, sorry, not basic definition of AVL tree. I want to talk about like what it means to have a good shape because we actually need some definitions. So there's a few ideas that I want to sort of talk about. The first is the idea of having perfect balance. Okay, so a tree that is perfectly balanced is a tree where the number of nodes in the left and right subtree differ by no more than one for all subtrees. Now, basically what we're doing is we're counting. So if I have a tree, here's an example of one. So this is a tree. We'll make it slightly bigger. Although the bigger I make it, the harder it is to maintain balance. Okay? Now this tree is actually perfectly balanced. In order for a tree to be perfectly balanced, every single node must have almost the same number of nodes in the left and right subtrees. Doesn't have to be identical, but it has to be almost the same. Now, if we take and by almost I mean off by one, okay? So that's almost. So over here, if we start the root and I count how many nodes are on the right-hand side and how many nodes are on the left, what I see is that there are a total of 6 nodes on the right and 6 nodes on the left. Both of those trees have 6 nodes in them. So at the root node, this is okay. Now, the problem though is that you not only have to check the root, you actually have to check every single node. Now, so the root is okay. So I'm going to just highlight that and say it's okay. Now, every single leaf node has no children, right? So the number of the difference between its left and right subtree, the number of nodes will be 0 because there's no children on the left, no children on the right. 0 minus 0 is 0. So these ones are all okay. We don't have to check those because they're leaf nodes. So we have 6 more nodes to check. Now, if we start by comparing, looking at this one, the number of nodes on the left is 2, and the number of nodes on the right is 3. So 3 versus 2, the difference is 1. We're okay. Then we have to also look at this node right here. Oops. This node right here, 3 on the left, 2 on the right, and so the difference is again 1. Looking over here, 1 on the left, 1 on the right, so the difference is 0, so we're fine. Looking over here, this one is 1 on the left, 0 on the right, so we're okay. Over here, this one is 1 on the left, 1 on the right, so we're okay there. And finally, this one is 1 on the left, 0 on the right, so we're still okay. So the difference, there can be a difference, but it cannot be more by more than 1. Now, so the problem, of course, with perfectly balanced trees is that this sort of shape is actually really hard to maintain. And even some pretty well-shaped trees are not perfectly balanced by definition. So for example, one of the things that we had considered was the idea of complete binary search trees. So over here we have a tree that is complete, okay? So this is something that we learned about when we talked about heaps, right? So this tree is a complete binary search tree. Oops, just realized that. Now, in this particular shape, um, we know that complete binary search trees have really good runtimes because the distance from the root to any leaf is no more than log n. So that is like really good because we don't have to travel very far to go to any node. And yet this tree is not perfectly balanced. If I take a look right at the root, the number of nodes on the left-hand side over here is 7. The number of nodes on the right-hand side is 3. So even though this is a really good tree, like if you got a tree that looks like this, you should be happy, um, it's still considered not perfectly balanced, which is somewhat sort of like, oh, well, I thought this was good. Well, yeah, it is, but it's not perfectly balanced. So what can you say, right? So while this is what we want, it's a fairly hard to maintain, okay? Because um, you have to it's fairly rigid. The definition also you can see that you can loosen it and really still not have a big adverse effect on your search. So we don't need perfect balance, okay? So while this is great to have, we don't need it. So what do we need? Well, it turns out that what we need, we can actually go with something called height balance trees instead. So a height balance tree, the definition, if you look, is actually pretty similar. The only difference is that instead of counting how many nodes there are, we count how tall a tree is. That's the difference. What is the height of the subtrees and what is the difference between the heights of the subtrees? So let's take a look at these two trees that I've drawn and ask what is the height of each of the subtrees um, in turn. So over here, and over here. So in the first tree, um, so the definition, similar to perfect balance, actually also has to be for every single node. So when we talk about perfect height balance trees, the definition is not only something at the root, it's actually applied throughout the tree. So keep that in mind. Now, in the case of the first tree, so first of all, any tree that is perfectly balanced is definitely height balanced, okay? Because you can't achieve perfect balance if it's not height balanced also. But effectively, we simply compare the heights of this tree. So this tree has a height of 3. That's how tall it is. The distance between the root of the subtree to its farthest leaf is 3. And over here, it also has a height of 3. So at the root, we're fine. 3 height versus 3 height, perfectly. So that is height balanced. And we can continue to apply this for all the subtrees. So at this node right here, okay, this node right here, the subtree on the left has a height of 2, and the subtree on the right also has a height of 2. So that's perfectly balanced. Okay. Now, let's take a look at one that is maybe a little bit harder to see. Over here, this one right here, the height of the left subtree is 1. The height of the right subtree doesn't exist. So any subtree that doesn't exist is 0 nodes tall. So this is the height is 0. So if we compare them, the difference is only 1. So what I'm basically saying is that this definition of height balance is done pretty much the same way as perfectly balanced trees, but instead of counting how many nodes, we simply say how tall are they. Now, what about this this complete tree we have on the right over here? This was not perfectly balanced, but this tree is height balanced. The height of the right subtree over here is 3. The height of the left subtree over here is 2. The difference is 1. Okay, the difference in height is 1 node. So that is perfectly allowed in a height balanced tree. Not for perfectly balanced, but height balanced, it's okay. And if I continue to apply the same comparison through each of the subtrees, I will see that the definition remains true. So like this is 2 versus 2, which is fine. And we can look at this for the entire tree and we'll be fine. So a height balanced tree and a perfectly balanced tree, the only difference between it is how do we define balance. Height balance means the height of the subtrees differ by no more than one. Perfectly balanced means the number of nodes differ by no more than one. Okay, so that's the beginning. This is where it begins. Okay, what we want is we want to have a way of saying, well, this tree is actually tree shaped enough effectively, and height balanced trees are tree shaped enough. Okay, so are they perfect? No, they're going to be taller than a perfectly balanced tree with the same number of nodes, generally speaking. But you can actually show that it won't be more than about 44% taller because uh, it's root 2. Okay, so effectively, so don't worry about it being taller. Of course, it's going to be taller. You allow it to be a little bit more off, right? But it won't be so far apart that it's unusable. Okay. Now, what does this mean? So height balanced trees, the definition of height balanced tree is simply that the difference in height between left and right subtree differs by no more than one for every single node. Now, um, a tree that is able to create height balance, maintain height balance, is a tree called an AVL tree. So AVL trees are height balanced binary search trees. So AVL is named after the inventors of the tree. And the tree is what is called an augmented data structure. So what that means is that when we actually go to implement this, we have to add a little bit of extra information to every single node within the tree. Okay, so an AVL tree isn't something that you can just like you can implement it without adding some extra information. Every node actually requires a little bit of extra information, and that extra little bit of information allows you to maintain this height balance. Okay, so we'll talk about that in the next video. This is sort of like just um, what AVL trees are. AVL trees are height balanced binary search trees where we maintain a little bit of extra information so that we can keep it height balanced. That's all it is, okay? So in the next video, what we're going to do is we're going to take a look at how do we insert into an AVL tree as opposed to a regular binary search tree, and how do we do it so that we can maintain this height balance, okay? So see you in the next video.